So something interesting happens, right? Because Alfvén actually becomes quite famous. He ends up winning the Nobel Prize for his work on magnetohydrodynamics. And Gareth pointed out something interesting to us the other day where he said that an interesting feature of MHD is that it assumes magnetic fields are baked into the fluid flow of the plasma. And by doing that, it, in some sense, ignores how important currents are in shaping those magnetic fields. And so he kind of points to this as a moment where the electrical aspects of the cosmos were, in some sense, able to be ignored because the MHD was so successful without actually bringing current into the discussion. What do you make of
Right,
that?
but the story is a little a little more complicated, excuse me. We'll jump over World War II and get into the 50s and especially into the satellite era. So during the 50s, we have Sputnik in 1957, and I was born in 47, so I was plenty old enough to remember this, and it was extremely exciting. And you know, to the rulers, it was alarming. If you could put a satellite in space, you could put a rocket into New York City. Um, but to everybody interested in science, people had been building up to this. Everybody had been aiming for getting rockets into space. There had been the International Geophysical Year. So this was extremely exciting. So the story I didn't know at the time, but was developing, was that the first satellites all had electromagnetic probes. So that was some of the first evidence people discovered that clearly space around the Earth was not empty. There was the Van Allen belts that clearly protected us from a lot of rather energetic particles that were floating around out there. Turned out, obviously, coming from the sun. And by 10 years after Sputnik, by the late 60s, these instruments had developed to the point where they could clearly detect in space exactly what Birkeland had detected on the ground. You could trace, as the satellite moved, you could trace the, you know, magnetic fields that outlined these vertical uh, currents that were aligned with the magnetic fields. So that was very exciting. And Alan Dressler basically pointed out, hey, Birkeland long ago and Alfvén today were right. And because this was what you call in situ measurements, it was essentially the same as laboratory measurements, except your laboratory was big as the Earth, it did become very widely accepted. I'm not sure Chapman was still alive, but certainly his theory was very rapidly discarded by everybody studying the aurora and the near Earth environment. And as Alfvén describes, now, of course, Alfvén's prestige, because he had been identified with uh, Birkeland's theory, Alfvén's prestige enormously rose. Second of all, Alfvén had been studying the sun a great deal. And he developed the MHD, the magnetohydrodynamic approximation, to study these waves in the sun, and it was very effective. But he emphasized that, like any approximation, it was only good in a certain set of circumstances. Now, one of the reasons why people went gaga over MHD is because it vastly simplified Maxwell's equations. Now, the fact that Maxwell's equations fit on a t-shirt and unlike general relativity, are actually very easy to explain. You can explain it in English language in a few sentences and be mathematically accurate. It doesn't mean that nature made them easy to solve. They aren't easy to solve. Nature doesn't have to solve them for them to exist. We have to solve them to make predictions with them. And the problem is that they're not easy to solve because if you look at the equations, the magnetic field is created by the electric currents. The magnetic field alters the direction of the electric currents. And all of this is not directly derived from the equations because the equations give what's called the divergence of the electric field. And the divergence of the electric field means basically it's related to the way the electric field changes with distance. And that's related to how the magnetic field changes with time. So you both have what are called differential equations, which are not very easy to solve, and these equations dealing with the divergence of the field. And from the divergence, you have to get the actual field.
Our videos come out of LPPFusion's research in fusion energy, which will power a future with abundance for all, with a clean, sustainable economy and environment. Goods, housing, and infrastructure would be extremely affordable once fusion kicks in. Fusion energy is the key to an advanced future. Support fusion research. The link's in the description. And thanks.
So all of this is very complicated. If you use the approximations in MHD, you get something that a computer can handle very easily. So since obviously by the 1960s and 70s, computers were doing a lot of the modeling of scientific work, that was a big advantage. So what was the limitation of MHD? MHD operated on the assumption that the plasma was collisional. A collisional plasma is the opposite of a magnetized plasma. In a collisional plasma, the magnetic field, while very important, we have MHD, alters the direction of charged particles in a time greater than the time for a single collision. So before a charged particle has the time to do one orbit around a magnetic field direction, it hits another particle. So the magnetic field only alters the direction of particles in the same way a slope alters the direction of molecules in a fluid. So it becomes an action on a collective fluid of fluid model, which is why it's called hydrodynamics, magnetic hydrodynamics, with a very close relationship to regular hydrodynamics. So why doesn't that apply in the rest of the universe? Well, stars are the only place in the universe outside of little planets like our own, not mostly plasma, in which the plasma is collisional. Now that's very important because stars are the source of energy in the universe. The fusion reactions in stars power everything else. But in most of the universe, the plasma is magnetized. So that means that the electrons move many, many times around the magnetic field line before they occasionally run into another charged particle and have a collision. That means currents can only move along the magnetic field lines. You can only get across the magnetic field lines. And again, we're talking about imaginary maps of very real things, which is magnetic field direction, when you have a collision. And if the collisions are very rare, the difference of the conductivity, the ability of current to move across the magnetic field and along the magnetic field, may be millions or billions of fold. So that completely changes how currents and magnetic fields operate. And of course, Alfvén emphasized it. He also emphasized that since currents are so important, you have to take into account what he called the global situation. All currents are closed loops because it's basically impossible for large amounts of charge to accumulate in a good conductor. And space is a very good conductor. So if you want to understand what happens in this part of the universe, which is part of a huge electric current, you have to understand what's happening in all parts of the universe that are connected by that same current.